Hey, this is Wyatt Greenwald, and today I'm going to be presenting combustion dynamics in a Reike tube, and just going to go over the basics of this. This is for AE 2610, and it's semester fall 2015. So what we have here is a Reike tube, which is essentially just a really long tube with a heat source near the bottom end, roughly a fourth of the way up the tube. And when the heat fluctuates periodically from the heat source, it causes the pressure in the tube to fluctuate periodically in the same phase of that heat source. And this causes what we call instabilities, and it's really important in studying combustion dynamics. Here is a basic outline of our experimental setup. As you can see, there's three pressure transducers that are about pretty evenly spaced from one another. And what this allows us to do is estimate the frequency and wavelength of the pressure and heat waves. And as you can see, you can pretty much look at it like an open tube. And our movable heat source allows us to kind of get a range of where our resonance will happen. We conducted the first experiment in a location for ideal resonance. Now, the second test was done with the valve open, which did not produce resonance. Third test was done at the 2-inch mark, which did not produce resonance. And the fourth test involved moving the burner until the resonance began and moving it up until it ceased. After igniting the burner, the tube was flushed with air to induce the resonance a little more quickly and get the experiment going a bit quicker. So one of the big things we measured here was frequency, and as you can see, there's some deviation between the estimated and experimental values. Our estimated value was around 97 hertz, while our experimented was a little more, around 110. And this was expected because we assumed the temperature in the tube to be room temperature. To give some reassurance, we had Georgia Tech student Christopher Tam with perfect pitch listen to the resonance frequency for us, and he estimated the pitch to be around an A2 flat, and with some additional research we found that that is right around 110 hertz, which is awesome. Here's a table of the pressure and PSI, frequency, and the phases from the first test. Now if you want to take a look at a few of these values, you can go ahead and pause the video and do so. So moving the mesh downward, we found that resonating happens right around 2.8 inches above zero, and moving it back upward, it begins to cease right around 5.4 inches. So there we can see that we have a range of roughly 2.6 inches where it's possible. So here's our three pressure sensors, and as we know, they were all about a degree out of phase in one another. And one of the things this will show us is the P node happens right around where the middle pressure sensor is. So that's where the maximum pressure value is in the fluctuation. So here's the photomultiplier voltage outputs for the first three experiments. What we're actually looking at here is the heat fluctuations for the three experiments. And it's quite apparent that for the first experiment, the heat was pretty chaotic, and that's apparent here. Now here's the heat output for the test one as a function of time. And as you can see, it started out fairly chaotic, and it began approaching a steady state value. Now if we were to let this continue, the resonance would eventually stop naturally because of the instability. Now this function gives us the heat output in time for the fourth test. And now what it really shows us is where the resonance happened as we lowered the heat source down to about 2.8 inches above the zero. Now as you can see, heat fluctuations are far more chaotic once the resonance begins. And you'll get to see that right here in a bit. One of the things we can conclude is the fluctuations of the pressure um, have a tendency to decrease with time and reach a sort of steady state. In the lab manual, we said that the pressure and heat waves were to be in phase of one another, and that's not exactly what we saw here. In fact, they're closer to being in antiphase than in phase. They were 164 degrees apart, making them pretty close to antiphase. However, this doesn't mean that they're going to destructively interfere to completely obliterate one another. They're actually still going to be a net positive uh, constructive interference that's going to go on. This is primarily because we're not quite in antiphase. We're about 20 degrees from antiphase. So that's why the resonance is possible and why we can get some pretty unstable results.